to our weekly colloquium here today. It's 4:02, so we're going to go ahead and get the show on the road. So I'm really excited to announce this week's speaker and this week's talk. But before I do, I want to get you all excited for next week's talk. And so next week's talk will be on some applications of the combinatorial Null-Stellan-Schnatz and the discharging method, given by Sogol Janabakam from San Jose State University. So be really excited to attend again next week. But for today's speaker, we have with us Dr. Kevin Moore, an associate professor from the University of Georgia. I'm really excited about Kevin's visit because I actually did my master's research in math education with Kevin. So I've learned a lot from him. I continue to learn a lot from him, and so I'm really excited that he's here today to share with all of us some of his work. So to say a few more things about Kevin, his research is focused on student thinking, particularly in areas of quantitative reasoning, function, and modeling. And in Kevin's spare time, he likes to play golf. He's an amateur golfer. In fact, this last year,
a month ago?
A month ago, he was in the USGA, United States Golf Association, mid-amateur tournament. So this tournament contains, it was new to me, but apparently it's a big deal because there are only 264 people that are invited to play, and the winner from that game gets to compete in the Masters Golf Tournament, which is it's like a big deal national tournament. Yeah, I learned all about this because he was my advisor. Like, what's that little logo with the thing on your hat? Oh, Masters. It's a big deal. So anyway, maybe that'll be Kevin next year. So good thing we have him this year to give a talk on representation and multiple representations. Take it away.
Well, thank you, Dr. Hobson, and thank you, everybody, for coming here on your Wednesday afternoon. So Natalie asked I do share a little bit about my journey before we actually get into the content of my presentation and would like to focus on today. So here you will see me in the top left. This was back way back in probably 2004 or so at the University of Akron, where I did my bachelor's and master's in applied mathematics. I ended up in mathematics somewhat haphazardly, but always stemming from my love of mathematics. So I actually went to the University of Akron to do engineering, found it very boring, and actually found the professors to be not very enthusiastic about their work. And so I switched over to applied mathematics, where my professors seem to love the work that they do, much like your professors here seem to be very passionate about the work they do, including working with students. During that time, I also happened to grow up in Ohio, so I love the Buckeyes, and you'll see I ended up attending this game, the Tostitos Fiesta Bowl, in 2006. That is the temperature on that's approximately the temperature on January 1st that year when the game occurred. As you can see, it was 76 midday. I was coming from Ohio, where I was dressed like that in about October. So needless to say, January 3rd, I walked over to the Department of Mathematics at the time and met with the grad coordinator saying, I want to come to school here. He asked me, he was really, really kind, really interested in what I liked, and I mentioned, like do numerical analysis, partial differential equations, math. I'm like, but I also got to teach this year, and I love that. That really intrigued me, and I'm like, are there teaching opportunities? And that time, very thankfully, he pointed me to Dr. Marilyn Carlson, who happened to land, I think it was about a $15 million NSF grant at that time, one of the bigger grants that they've ever released to mathematics education. So she was looking for workers and worker bees, and I just happened to finally get her on the phone, and she said, well, come work for me. We'll try it out, see if you like mathematics education. And during that first year, I learned all about problem solving, including Poya, as well as the work of Marilyn, Pat Thompson, and some other people. And I gravitated immediately towards it. I was like, wow, you can actually take an analytical lens, a mathematical lens to math learning. I'm like, yes, this is exactly what I want to do. So I jumped on board, followed the problem-solving route, ended up in the world of trigonometry. If you take a look at my earlier work, it was all within that context and thinking about how students reason about angle measure and trigonometric functions, and really trying to reshape instruction around those major ideas. That's ultimately what I produced my dissertation, which somehow landed me the job at the University of Georgia. I'm still not sure how I ended up there, how they let me through the doors. But I've been there 9 years now, and today I will be presenting on all the research we've been doing in the last couple years that Dr. Hobson back there has been a part of. All right, so I believe Natalie is going to pass out a sheet for me. So I want to return to the opening animation. And I have a task I'd like you all to work on. I know some of you have seen this task before when Natalie has given a presentation. But to get us all on the same page, I do want each person to engage in it. So if you've seen the task before, don't spoil it for the other people. Let them work through it. And for those of you that this task is new, take a look at your prompt. I'm going to give you about 5 minutes. I'm just going to roam around and listen to conversations. Feel free to talk to each other and work with each other on this, or work in isolation, whatever you're most comfortable with. But think about this task, and we're going to use this as our springboard for the discussion today.
I assume he means distance along the road. I don't know. Oh,
What's sneaky about it?
I haven't seen it. When you say distance, you're talking about distance along the road or distance?
I used to be at the road.
Right, so you're going up. Okay. I give you an animated. So I
All right, make sure you maybe share with your neighbor, talk a little bit, and in about a minute or two, we're gonna proceed.
Right, so think about zero units from atoms. This point is at zero. So this point will tell me I'm 0 miles from atoms. 0 miles from so you're not there. So when you start, you're definitely 0 miles from atoms. And that's what this line represents. Because as I'm going up this way, it says I'm getting farther from atoms. As I'm going this way, it says I'm getting
farther. So your distance this way is getting closer, and this way is getting closer. Okay? So, yeah, so we're going to start doing that. We'll start 0 miles from now and some distance. Can you see what I'm doing?
All right. I hate to stop you, but we do need to, I would like to show you some data today and talk about some things. And does anybody want to make any general observations, though, about that task and maybe your last 5 minutes of engagement?
I'm sorry,
Any general observations about your last 5 minutes of engagement or about the task?
It's hard to graph this, really, because it breaks the rules, or the habits.
Who would agree that it's hard to graph this because it breaks some rules? Okay.
It depends on what's the function of.
So say a little bit more. It depends a function. What's a function of what?
Well, the thing is, the distance from Gainesville, what's in that circle, that's a constant. But the distance from Athens is going to be different. Okay, so, and functions don't work that way.
So something about function here. Now I would contend, and we'll get in this a little bit, this has very little to do with function. It has everything to do with function as well, but it also can be thought of as having nothing to do with function.
Right.
I think a lot of the time, a lot of graphs tend to have some time piece to it, which means that, like, you know, time is always progressing. So it's like time with distance, but this is distance with distance, so it doesn't.
Yeah, so how many people caught on that? I removed time from the situation. There's a distance versus distance graph. It's not something that's very normatively seen, at least in the math classroom. Moving to like an engineering context or a physics context, you might see a little bit more frequently. But. Okay. So we're going to return to this task in a little bit. I'm also going to show some data around it working with a couple students. But I want to give a disclaimer before I move into this task. Conventions are not bad. Despite some of the things I'm going to say in today's talk, I do not want this to be the message. I would not agree with that statement. I removed the not. So conventions are not bad, but I'm going to return and contextualize this claim too later. Under what context is this claim appropriate, and under what context would saying conventions are bad be appropriate? Because really conventions help us function in mathematics, right? They give us very succinct ways to represent ideas. They give us a way to convey mathematical ideas to each other in very convenient ways. They also help us have a huge conceptual offloading, right? I can take something and write it like this, where I'm trying to point out, hey, there's some relationship between an angle measure or an arc measure in radians relative to a half chord measured relative to the radius. And I can just write that to try to convey it or to capture my own thinking. Also, with the numerous representations that we've developed, it helps us move very flexibly within our own thinking and develop a lot of different mathematical ideas from that by this conceptual offloading. So conventions give us a lot of power in mathematics, especially as we run forward into doing more advanced mathematics. And I'm sure we all notice a phenomenon of just how important conventions are when we do move into different conventions, right? So this is from Dr. Hobson's class yesterday, in which they were changing base systems and moving to more non-conventional base systems, which bring out some important mathematics. So one of the things I contend is the phenomenon of how difficult things become when we change conventions is actually really, really important. And there is a cognitive affordance to that we need to think about when we're working with students. Regardless if that's our students in our K through 12 classrooms, our students that are going to be teachers, or our math students at the undergrad or graduate level, that this phenomenon is actually really, really important. It's something we need to observe more often in our mathematical instruction. And I'm hopefully going to give some ideas on that by the end of this talk. If you buy them or not, that's a different question, but I'll at least convey them. All right, so I also stole from the Colloquium announcement this nice image here. So who's seen this image around the idea of function before, or something like it? Decent amount of people, right? Function is one of the more popular ideas in which we discuss multiple representations, right? But as we all know, especially working with students, that the idea of these being multiple representations can be very problematic. That can be very difficult. And this is pervasive in the mathematics education literature, that multiple representations is a hard thing. And Pat Thompson summed this up very nicely all the way back 20-some years ago, where he made the claim, I have seen no evidence that there are multiple representations of anything to students. Right? So what Pat was pointing out in in his 1994 paper that has been reiterated in mathematics education and literature throughout the last 20 some years is, often when we think about multiple representations, they're often very isolated in our students' thinking. That there are different games to be played with each one. So yeah, I can do some things here, I can do some things here, I can do some things up here, but they're often disconnected in those things that we do there, so they become isolated topics. And that's actually captured pretty nicely if we even think about this statement. So we'll see this in textbooks all the time. They'll say relations and functions can be represented in multiple different ways, but rarely does a textbook or a piece of literature define, well, what is being represented in different ways. Just saying relations and functions doesn't convey meaning. It doesn't discuss the meaning of function or relations that should be represented in certain ways. How do we conceptualize these objects that would let us see all of these things as the same? So, returning to that task, I would like to identify one way to think about relationships and functions that does give us a way to think about something that's represented in multiple ways. So, if we return to that task, this is a nice little dynamic image that can convey and capture what a normative graph would end up looking like underneath the axes orientations that I gave you. So we'd end up with something that looks like this. Now I point out a couple features about this relative to what's being represented here, right? So within that image of the situation, I've explicitly identified that there are two magnitudes that we're thinking about here, two segment lengths. And those segment lengths are measurable, right? That we can think of them quantitatively as things that we can measure. Now we don't need to think about specific measures of them, because we can assign different unit magnitudes which would come up with different measures. But we can merely just think about them as magnitudes themselves that could be measured. Now, another thing we can think about is how those change together as that point moves along. So when we're along this part of the path here, was so nicely identified earlier, our magnitude from Gainesville stays constant, while our distance from Athens continues to increase. Then as we move along this path, well, there we have the constant rate of change. That's actually 1-to-1, where any increase in one magnitude yields the same increase in the other magnitude. So we have this beautiful dynamic relationship that we can think about the situation. Then one of the powers of mathematics is we can create another representation that shows the exact same thing, right? So we can transform those magnitudes, orient them in different ways, produce a point, put some pixie dust on it or whatever you want to call in terms of the imagery you'd like to see, and we create a trace that gives us the same relationship that's created by those magnitudes. This is what Marilyn Carlson defined as co-variational reasoning in her work with several colleagues, where she defined it as coordinating two varying quantities while attending to the ways in which they change together, right? So conceptualizing two things that are measurable. Now let's think about how they move dynamically into different mathematical properties of that. And Pat and Louis Saldana also have done a ton of work in this area. And one of the important things they pointed out that's often overlooked is what they call the conceiving of a multiplicative object. Now, this isn't multiplicative in the sense of multiplying, like 3 times 5 gives 15. But this harkens back to Piaget's idea of multiplicative, so adjoining, right? That, hey, I can produce something that is simultaneously one and the other. The best example is a coordinate point, right? So if I choose that point, that's really the joining of a magnitude and a magnitude to produce that. And it's within that world that we can think about two things being a multiple representation. That there's this quantitative relationship, this co-variational relationship that we can conceive in both situations, and that remains invariant amongst the transformations we might make from one situation to the other. And so that's the idea I'm going to run forward in terms of function or relation as we move forward this talk. If I use those words, that's what I'm implying. That's what I'm implying from that. This quantitative structure that we can construct in our mind of two things that are measurable and how they change together. Now, based on those ideas, my team, including Natalie, have thought about, okay, well, that's what we'd like students to reason about. But obviously, that's not always going to be the case. So first, we start with the fundamental question is, to students, what does a representation represent? So when they see a graph, when they see a formula, when they see, you name the representation, what is it that they see as being represented? And is it something that could be represented in multiple ways? And then, of course, one of our major questions in terms of developing instructional materials and investigating learning is, how do we support students in constructing co-variational relationships as something representable in multiple ways. And it's really the last 5 years of a project that we've had that we've dived into these questions. Obviously, we've had multiple questions emerge from these, but these are our overarching questions. All right, so I'm going to go ahead and jump into some different tasks and data that we've used in our investigations. I'm going to show a couple of things that we've found, and then I'll move into what we're doing based on those findings. To give just a little bit of context, I'm happy to talk after the talk with anyone about specific studies that we've done and point to some different specific studies, but we've done a lot. We've done clinical interviews, so settings where we're not trying to promote learning, we're just trying to figure out how people think, with undergraduate students, high school students, graduate students in math and mathematics education faculty. We've done teaching experiments, so imagine sort of interview-styled settings where we're trying to promote growth and learning. We've done that with primarily undergraduate students, so at the undergraduate mathematics as well as undergraduate mathematics education students, including those that are going to be pre-service teachers. And then we've also done online surveys with in-service teachers, where Jason Silverman out of Drexel University has helped lead that aspect of the project, where we're trying to extend our findings that we're seeing with pre-service teachers to see if those show up with in-service teachers as well, and trying to do that in ways a little bit more convenient to getting, if you want to call it, big data, to see if we see anything there. And we'll be talking about any of that data in this talk, but I'd be happy to share some of that and discuss some of the findings there. Now, the contexts that we've used have not only been these nice dynamic contexts, right, because we're trying to promote co-variational reasoning, so we want to include dynamic situations to help engender that. But we've also used what we might call static situations too, some more traditional types of problems with just presented graphs and presented relationships as well. And I'll be presenting a little bit on both of those today. Okay, now as I present some data around some of the different tasks, I want you to be thinking about these two questions. So what do the students' actions imply they're representing? So as the students are discussing things, what are they discussing? What is the nature of the object that they're talking about? And then think about what role conventions might be playing in their thinking. There's a reason I use quotations here, which I'll touch on later. But for now, just what role might conventions play in their thinking? All right, so here's the first task we're going to start with. I'll give you a half minute here to read it and think about it. Okay, now with that problem, we do have the follow-up prompt. So the way we present this in an interview to our students, we let them respond, think about that, exhaust basically everything they want to say about it, and then we follow up with this prompt. So I hear some hms. Right, this is actually rather ingenious, and this is really the fundamental underpinning of inverse functions and relations. Because if I write it as y equals sine x, that should necessarily imply, obviously under certain domain and range restrictions, if we care about one-to-oneness. Of course, go back to previous in 1955 or so, and that didn't matter at all, right? Inverse relations and functions, that wasn't quite the concern until we needed to formalize things around the analysis and different calculus ideas. But y equals sine x necessarily implies x equals arc sine y. Right, if we can write that, we can certainly write the other one. And I've even provided the appropriate restrictions for x there over which that has to hold. So essentially we're saying, okay, can our students, and these are with pre-service teachers, acknowledge that that is appropriate, right? That, yeah, that flies in the face of some conventions, but that is a mathematically correct statement there. So we're going to take a look at some different student responses to that. Hopefully the sound works on these. And so these student responses are after we've slid the second part to them as well.
I'm thinking this just kind of looks like sine graph, like the plain sine graph, which is going to be different. So, yeah.
feel like he's missing the whole concept of a graph.
Just say a little bit more.
Like, I know you can call whatever x is, you know, if you're doing time and weight or volume or whatever, like we can flip-flop those and, you know, be okay. But not necessarily with the sine graph. Like a sine graph is like a, I mean, it's a graph like everyone knows about, you know?
Okay.
If that doesn't help the situation, that doesn't mean you cannot do it now. But that's just, no. I think they're just missing the concept of graphing.
Okay, so hold those responses in mind, and we're going to take a look at another example. As background for this student, so student got the first part and said, yeah, this is perfectly appropriate. So we slid the second part, and they said, yeah, that's exactly how the student could be thinking. He even wrote down different equations. So there's the y equals sine x, there's equals the x's arc sine y. And so this one we actually tried to torpedo a little bit, and we passed the conventional arc sine graph to her, so what you typically see in a textbook, and said, well, what about a student says, hey, my teacher always said this was the arc sine graph, you know? Like, what do I do in that case? And she described, well, you know, I would show them they're the same thing, and she identified a few points to say, like, look, these points match up. So pi has 1 is on both graphs, use 0, 0, I think, and one other one. And then we played the skeptical role and said, well, you've only shown us a few points, like, okay, 3 points match up, but what about the rest of the graphs? And this is her response to that.
Measures. So it's like here, with equal changes in angle measures, my, sine vertical distance is increasing at decreasing rate, and then show them here it's doing the exact same thing. With equal changes in angle measure, my vertical distance is increasing at decreasing rate.
Okay.
So even though the curves, like this one looks like it's concave up and this one concave down, it's still showing the same thing.
So we see pretty stark contrast to the previous students. And she even went on to mark up her diagram showing partitions and how things change together. So for equal changes in angle measure, we see increasing decreases in what she calls a vertical distance. Okay, so to summarize, one way to think about the the two students' activity, is essentially in a very indexical way. The sine graph or the sine relationship is this image, right? It's going to look this way. And because it's named to that, it's pretty much in a one-to-one correspondence in its name. This graph is a sine relationship or sine function, and the sine function is necessarily this graph is this shape. Now, what I don't mean there is that the student couldn't unpack it into coordinate points or anything like that. But that graph did exist essentially in a one-to-one relationship with a named function, and that is what it is. Now we compared that to the second student, and the second student's focus was very differently, or in a very different place. The second student's focus was, well, how do these things change together when I look at this graph? I can unpack that in terms of coordinate points, or I can think about, okay, actually, how do these change in magnitudes, and what covariational relationship do I get? And you even heard the way she discussed, she was actually discussing quantities in that case, that essentially enabled her to see a quantitative relationship across the two graphs, right? So this same relationship that we could write as y equals sine x, or x equals arc sine y, either or, but regardless, we have quantities changing in a certain way where equal changes in one would yield increasing decreases in another, at least for the portion of the graph that she considered. All right, we're going to take a look at a second example. So this interview task, these were also done in clinical interviews. A hypothetical student is graphing the relationship y equals 3x, and this is the graph they provide. So I'll give you half a minute here to think about how a student might produce that graph. So there are actually a lot of different ways that you could come up with a viable explanation for the production of this graph. Some of which may be problematic. For example, a student mixing up rise over run, right? So they've learned a rise over run technique, and they run 3 rather than rise 3 and produced a graph like that. They just confuse the 3 and 1. There's other ones they come up with. But then there's one that some come up with, but that we provide in a second prompt, much like the first one. What about a student that clarifies that? right? So they just chose to put y on the horizontal axis and x on the vertical axis. Then we do, from our perspective, the way we design this task, do have a mathematically appropriate relation or representation of y equals 3x by doing it that way. So we'll take a look at a couple students' responses too after they've been given the second prompt. So we see this student, the first prompt, rejected it as, or she came up with the rise over run error. So this is produced by a rise over run error. And then we gave the second prompt and said, okay, the student didn't like, we even had the student's grade here. I think she wrote down a 6 out of 10. So the student didn't like their grade at all, clarified their axes. Now what do you think about their solution?
Sense. I mean, the only way they do it is like this, and it's still wrong because this is negative slope. So I would just explain to them like the difference between the x and y axis, and explain to them the difference, because if they were thinking of it as like sideways or whatever it is, or inversely or whatever, then show them like the difference between like positive and negative slopes also, because that's something that like when I was like in middle school we like learned kind of like a trick to remember like positive, negative, and no slope and 0, like that's where the slopes were, and it's like stuck with me till now. So it's important to like know which direction they're going when it's positive and negative, and 0 and no slope too, but in this case positive or negative.
Okay, good.
Now we'll take a look at that and compare it to a second student's work. This task was a little bit different in that we provided what we called a naked version of this task. So you notice there's not even numbers associated with this one. Same prompt, the student's graphing y equals 3x. This is the graph they provide some viable x, or what was the student thinking. This student, where we're going to be jumping in on where the student's at, she had identified a lot of different options for this, including multiple directed orientations. So for example, you could do y here, x here, and have different positive and negative orientations that would yield y equals 3x. And she had, even at this point that we're going to jump in, had identified, well, I normally do it like this. This is how we would normally do it. And so what we did in response to that was ask her, well, what about someone coming along that says that has to be negative slope? Essentially the previous student's claim. Like this is sloping downward left to right, that has to be negative. How would you respond to that student? And this will be her response to that.
You'd have to notice that even though it looks like a negative slope, because we call it slope because it's visual and it's easy to visualize a negative and a positive slope. But that's only visual on our conventions of how we set it up. But like, if slope is rate of change, we can still see that for like equal increases of x, we have an equal increase of y of 3. And so for equal positive increase of 1, we have an equal positive increase of 3. And so it is a positive slope.
So if we think about contrasting these students' behaviors here and what that might imply about their thinking, and that first student was very focused on the direction of a line and making the slope associations with that direction, much like in the previous case, the first students that we looked at, sort of what we call indexical associations. This looks like this, it's this direction, that would be negative, and that would have to be positive slope. And even some students even talk about in terms of movements. Well, if I move up and to the left, or if I move down and to the right, that has to be negative, or if I move right and then up, or down and then left, that has to be positive slope. And if we compare that with the second student, much more of a dynamic quantitative focus. After even noticing, well, we could think about slope in a more visual way and make associations from that, but if slope means rate of change, that means I have to look at how things are changing. And what we have in this graph is something along these lines. And she, as I mentioned, she even talked about a normative graph that she went on to draw later and talked about, well, look, this shows me the same changes. And I can think about it just as appropriate with that, but she kept y and x oriented in that way. So much like the previous task, we can think about the second student as having to focus on something a little more abstracted, right? That there's this relationship I'm trying to show, and I can do this in multiple ways, but I'm still preserving a quantitative invariance here as I do that. All right, now I'm going to move back to the task that we opened up with, and I'm going to show the case I like to call it's backwards case. So to give a little bit more context about this task, we used it in a little bit different way in our interviews where we actually had the students graph on axes as they wanted to, so they could construct axes from scratch, and we posed it as total distance traveled. So think as accumulation. So as I travel to, and then as I travel back, when I'm traveling back, I'm still accumulating total distance traveled. Where distance from Athens, right, as I travel back is now decreasing. The first version of the task allowed the accumulation of it. So on the student I'm going to present some data from, this is her solution to the first version of the task. And we see it's a normative solution. Now this took some effort for her to construct, so I don't want to act like this was done in 2 minutes. But as she worked through it, you can see even the partitions that she drew. She talked about equal changes in total distance would yield equal changes in distance from Gainesville. Along the semicircle, my distance from Gainesville is constant, distance traveled still increasing, and so on and so on. A really nice quantitative focus in terms of her production of that solution. And now we're going to jump into her activity on the version of the task that you all worked from. What she's done at this point, she's trying to create an initial point. First, she put a point along here, along the vertical axis. Then she said, well, I want my distance from Athens to be 0. Moves a point back down to here. And then like, well, maybe it's up here, and we're going to see her wrestling with that a little bit.
Well, I want to start here, but that would mean that that's 0 as well, but you're still... I want this to be decreasing. Can I make that decreasing?
So what do you mean?
Because I wanted to start here because I wanted to show that the distance was decreasing, but that means your distance from Athens is decreasing, and as you're getting, but your distance from Athens is growing, but your distance from Gainesville is decreasing. So if that's growing and that's decreasing, so. But you're starting at a distance of 0.
So one thing I want to point out here is take note, she has the relationship in mind that she wants to represent, right? This is not an issue of she doesn't know what she wants distance from Athens and distance from Gainesville to do. No, distance from Athens is going to increase as distance from Gainesville decreases. So we're going to take a look at, this is jumping forward just maybe 30 seconds to 45 seconds. We're going to see her continue to work through this problem.
I would like it better if it was distance from Gainesville on this side and distance from Athens here. Because if your distance from Gainesville, you're that, and it would just go like that. Because your distance from Gainesville is decreasing, but your distance from Athens is increasing. I honestly have no clue. I don't know why this is so hard, why I'm struggling so much with this. It's hard to say that as something is decreasing, something is increasing.
So take note of her last claim. She actually just said that. There's a little skip there that's about a 1 minute skip. But she had just said that relative to this graph, right? So when she says it's very hard to say something is decreasing as something's increasing, really what she's talking about under what you've presented to me orientation-wise, I'm not really sure what to do with it. So now we'll jump forward about 6 minutes later, because a response we get to this often is, well, we just show her the initial point. It's easy, right? And I think for a lot of people in this crew, once you got that initial point down and realized what that was, it was actually pretty natural to think about, okay, what happens? But that's not always the case, and typically not the case when we're working with students. So this is after about 7 more minutes of just what we call productive struggle, where she's just really wrestling with what to do here, right? How to represent this relationship. And we've now asked her a little more pointed questioning, including about an initial point. We'll see where something clicks for her.
Ooh, what if I send it like here? Okay.
What makes you think that?
But I don't want to start, I don't like starting graphs. I don't know, work backwards, that's weird. So as your distance from Gainesville decreases, that increases. So it's like I guess I just don't like this.
Why don't you like it?
Because it's backwards.
Is that backwards would mean?
Backwards, it's traveling from right to left. But I think my graph is just, I think I'm just not clicking. I think I'm missing something.
So it's really interesting, right? Her reasoning there was beautiful, right? With the initial point, like, oh, as distance from Gainesville is decreasing, distance from Athens is increasing, and she draws a trace to think that exactly the type of reasoning we're seeking and looking to foster. But she ended the task by rejecting that solution because it's backwards, because I drew it from right to left, because that's not how graphs work. And she even had a beautiful quote where she even mentioned, well, this is sort of right, but no, it can't be this way, and that's where she went on. This is not clicking, right? I'm missing something here. In lieu of time, I'm going to skip over our students. And this one, she just kind of fluently goes by graphing, doesn't even acknowledge it being weird. I was just going to use it as a contrasting case. But I do want to get to sort of what's the point here. All right, so let's step back for a second. So what I want us to think about are what were the underlying themes and differences in students' meanings here? And then what task features helped uncover these differences? So does anybody want to offer initial thoughts on that? Does anything stand out to you? I, of course, have plenty of ideas about what stands out to me, but...
I mean, I think one of the things that really shows up is that there's a right way to do it, sort of thing. There's something that this is not what I'm supposed to do. You're breaking the rules somehow by doing exactly what the task is asking you to do, and that causes a lot of cognitive discomfort.
Yeah, we see very explicit cognitive perturbation here, right, with these students of things that we're not supposed to do. So very much like math is a set of rules sort of idea.
Yeah.
Other observations?
I mean, to me it seemed like there was a lot of right, left, up, down versus this co-variational reasoning. And I feel like we often take right, left, up, down kind of talk as indicative of understanding that co-variational reasoning. And this is a little alarming.
Yeah, very good observation. If we think about how calc is typically taught, if you look into a calc textbook that speaks to curvature, you will see a lot of sort of movement discussion, graphs curving up, curving down, right to left sort of ideas, right? Including a lot of anything that's tangent line based is often going to speak in that way. Any other observations people would like to share?
It's like you're just kind of disrupting like the first step that a lot of students have. They've been trained to have to take a couple first steps in a way to view a problem, and you're just not letting them. That first couple steps aren't working for them, and then they don't have an alternative. So then they just kind of go into the pool of struggle.
Yeah.
Just kind of this disruption of training that they have.
Yeah, we're sort of messing with tricks is one way we like to phrase that, right? Sort of torpedoing ways of thinking we know they're going to bring to the table. And then the question becomes, do they have ways of thinking underneath that they can fall back and rely on? And then the extra question is, if they do have even those ways of thinking, like we've seen in that last clip there, do they acknowledge that, going back to the point of mathematical rules, or do they acknowledge that as mathematically correct or not? Or does that somehow like disrupt how we're supposed to do mathematics, or is not relevant?
So that raises another question. Have you tried this out with people who don't have good, strong background in graphing and functions?
Yeah, and I can comment on that too, and I will. Let's return to that at the end, because that's a really good point. But yeah, in terms of this, so one of the big observations is going back to the point of, okay, what are students think they're representing, right? And we see a lot of focus on how things look, including how we draw things, right? So even a kinesthetic motion of drawing a graph, well, how do we do that, and how have we been trained to do that? And if we disrupt that or void that, then it can't be mathematically correct. Versus the quantitative focus, right? Like, well, this might be peculiar or different than how I normally do things, but hey, it captures what I'm trying to do quantitatively, so that gives me mathematical correctness. And of course, one of the things that we noticed from these tasks and why we designed them to be that way, we did that intentionally, right? That some of these task features, by messing with what we saw as conventions, that brought these things to the surface. It was actually completely random how we ended up on this research path, and I'd love to talk about that. But it was really because students did this one time, and everybody else in the class did not like what that group did. Like the rest of the class literally rejected them having an accurate solution because they played with conventions, and that led us down this road. Okay, so let me return back to this claim. Conventions are not bad. I hope I've convinced you a little bit that they can be in some ways, but I still would say conventions are not bad. The key word there is I'm using convention as a convention. With respect to a lot of those students, what we would call convention was far from that, because there's critical criteria for something to be a convention, and there's lots of different ways you can define it, but these are what we break down into something that's operational in terms of what a convention has to be. So a person understands something a convention. Again, conventions are personal constructs. They don't exist independent of those of us that are reasoning, because we can change communities and conventions change, right? What we see as a convention can change. So there has to be a few things in mind. One, a concept, right? Something has to be being represented. There has to be a convention around something. A community of individuals, right? Conventions exist within interaction. And that can be anticipated interaction too. That could be me in my room creating something new and thinking, I might show this to people. What do I need to do to show this clearly? And some representational practice that he or she perceives as a choice in that community among a variety of equally valid choices. There's a key aspect along that last part. It has to be among a variety of equally valid choices, right? That for something to be a convention, the other options have to be equally valid. Because if they're not equally valid, then it can't be a convention. Convention is arbitrary by definition, by the Webster's dictionary. It has to be arbitrary. So there has to be other ways to do it that we can acknowledge as correct. That doesn't mean they aren't going to be problematic if we try to go interact with someone. Of course, if I start doing things in weird ways that are mathematically correct, I'm going to run into problems interacting with you, and we're going to have to hash this out. Well, this is why I'm doing this, and this is how I'm doing this. But it means we could get to the point where it'd be like, oh yeah, that is the same mathematical structure that I do in this way. I can see it there too, but stop doing that because you're going to annoy everybody else in the field, right? And there's a few ways in terms of our work that we like to define these that have really done work for us, both instructionally and in research. So if we think about a concept, and this wraps up convention within it, understanding a concept involves constructing and differentiating between what's mathematically critical to it and what is merely a practice of representation. That's something we use when we're thinking about concepts and working with students, that we have to think deeply about this as instructors or researchers or mathematicians even, that's key. What's part of the representation I'm using versus what is actually critical to the mathematical idea. And in terms of the specific context we work within in terms of co-variational reasoning, we call our concepts extractive quantitative structures. So that's when we've constructed a co-variational relationship that we can act as if it is independent of any representation of it or any specific instantiation. Of course, we're always constrained to having to show something if I want to show you the relationship. But much like those students in the way they were talking, there's like they were thinking of something independent of their activity that they were doing, right? That there was something bigger than that. And then a big real key aspect is that what's supportive there or generative is that structure can be called upon in new situations, right? If I come across a buoy that's bobbing up and down, I'd be like, man, that kind of looks like a sine relationship because I have something periodic here. And I have a chord length that I could think about. And if I map time onto it, oh, I got the sine relationship, right? It's something that can be enacted in novel situations. Let me skip forward. Now, on the second part, again, I want to emphasize this idea of equally valid choices. So if we think about that student's discussion, that's exactly what she captured, right? Well, we do it in these ways because there are some benefits to this in terms of like visually assimilating the situation, but I could do it in these other ways. I would just lose that quick assimilation, right? This quick conceptual offloading I would do. That's an important part. Okay, so let me wrap up real quick. Just to say like what to do with all this. So the things that we found to be important in designing instruction or research, if you will, in which we think very hardly in our group now, we look to identify a concept as an instructional goal, right? So we really sit down hard and think about this mathematical idea, what's specific to the representations that we're using, and what's actually critical to holding together those ideas. So saying a function has multiple representations is meaningless, we have to sit down and think about what do we mean by function? What are the mental actions there that would help us connect it? Covariational reasoning is our answer in that world. Then we got to design a series of different repeated experiences for students to actually reason in ways that are consistent with the concept. Just giving students graphs in one orientation is not going to do it, because they're not getting multiple representations from that. They're not giving an opportunity to construct multiple representations for themselves. And another key part of that is if you don't give them different representational activity opportunities, as an instructor, you don't get to see, are they constructing the concept or are they constructing something where conventions are embedded within their thinking? If we always keep input on the horizontal axis, some of those things we saw in those videos will never come up. So we call that the under the radar phenomenon, where students can fly under our radar if we don't push on these things here. So as one last video to show you what this looks like before I open things up for questions. Something we've learned, or what we love to do, and this is kind of a disappointment that the Common Core removed polar coordinates from these standards, because we find it critical to use polar coordinates because it's another coordinate system, it's another representational context. And this will give you an image of what this can look like as these students wrestle with, it's hard to see, but there's a circle there, that's the r equals sine theta. We're seeing them wrestle with, they think it's r equals sine theta, so they drew y equals sine x, or x equals sine y, wherever you put x and y, and they're going to wrestle through why this is r equals sine theta.
Well, this is 1 here.
Which would be our radius.
And then this gets us from 0 to right here is 0 again. So we start here.
Yeah, and you're sweeping around because our theta is increasing. Distance from the origin increases and then decreases again.
Because you're saying that theta increases and distance from the origin does what?
It increases until pi over 2 and then it starts decreasing.
And then it starts decreasing. Okay. And then what happens from like pi to 2 pi?
Same idea, except the radius is going to be negative. So it gets more in the negative direction of the angle we're sweeping until 3 pi over 2, where it's -1 away, and then it gets closer.
Okay, so from like 3 pi over 2 to 2 pi, can you show me where in this graph it would go start from and end at?
Yeah, 4 pi over 2 there.
This is the biggest sine in magnitude then, so it's the furthest away. And then it gets smaller in magnitude.
So we see that's what we think of in terms of multiple representations, right? They're engaging in activity that they can see as quantitatively invariant amongst, if I'm down there or I'm over here. All right, so I will stop there. I do want to say thank you to my lovely team. This is a subset of most of the team members. You'll see Dr. Hobson up there, as well as 3 of my current grad students in Biao, Irma, and Halil, as well as Hamilton, who now is at Texas State as an instructor, San Marcos. So thank you, and I'll take questions.